The locomotive left York just before dawn, a 262T wheel arrangement on paper, something else entirely in practice. The freight consist behind it ran to over 400 tons. Heavy goods. Long grades ahead on the run south toward Hull. The locomotive working this service was not a conventional steam engine. It was not a diesel locomotive either. The men at York Shed called it the Kitson still. The railway had not ordered a fleet of them. There was only one. That was enough to know what it could do. What it could do was unlike anything else moving on British rails in 1933. The engineering principle it ran on, a double-acting cylinder with steam working one face of the piston and diesel combustion working the other, was so far outside the standard models of railway engineering that most of the locomotive department could not fully explain how it functioned. A century later, that remains true. This is the Kitson still, the hybrid locomotive that solved the diesel transmission problem before anyone else had an answer, that burned fuel at 1/5 the rate of a contemporary steam engine, and that was scrapped without a single production order ever placed. Nobody remembers it. That is what this channel is for. After the First World War, British railway companies faced a cost calculation that would not balance. Steam locomotives were familiar and powerful. They were also enormously wasteful. The thermal efficiency of a standard steam locomotive of that period sat somewhere between 7 and 10%. For every unit of energy in the coal burned, 9/10 was lost. Through the chimney, through the firebox, through the surface of the boiler, through every exhaust beat. The railways knew this. They had known it for decades. What they could not do was fix it. Diesel traction offered a theoretical answer. But in the early 1920s, the problem of transmitting diesel engine power reliably to the driving wheels had no satisfactory solution. Electric transmission, the system used in virtually every modern diesel locomotive, was still immature, heavy, and expensive. No major British railway company had found a workable path forward. A Leeds locomotive builder, Kitson and Company, had a different idea entirely. Their answer did not come from the railway industry. It came from a marine engineer named William Joseph Still, who had spent years looking at how much energy conventional engines threw away, and had filed a patent in 1917 describing a way to stop doing that. Before we continue, if this kind of railway history matters to you, consider subscribing to the channel. Every video here is built around the locomotives and railway systems that the standard histories overlooked, the machines that outperformed their celebrated counterparts, the engineering decisions that were ahead of their time, and the railway lines that shaped nations without receiving the recognition they deserved. If that is the kind of documentary worth watching to you, the subscribe button is how you tell us. And we want to hear from you. Did you work on the railways? As a driver, a fireman, a fitter, a signalman, a track engineer? Did a parent or grandparent spend their career on a railway that is no longer operating, on a locomotive class that is no longer preserved, or in a workshop that is no longer standing? Leave it in the comments. The people who actually operated these machines know things that do not appear in any published railway history. We want to hear from them. Now, back to the locomotive. Still's patent described a double-acting cylinder that would run on both thermodynamic principles simultaneously. The inner face of the piston, steam, supplied from a small oil-fired boiler. The outer face, diesel combustion, fuel injected directly into the cylinder. The same mechanical stroke served both processes at once. And critically, the diesel exhaust gases did not escape to atmosphere. They were routed back through tubes in the boiler, heating the water, producing more steam, completing a thermal recovery loop that no other locomotive design had attempted. Kitson built this into a locomotive, works number 5374. The Eller designated it KS1. The machine had 8 horizontally opposed cylinders arranged in 2 banks beneath a compact cylindrical boiler. Bore 13.5 inches, stroke 15.5 inches. The crankshaft drove a jackshaft geared at a ratio of 1.88 to 1, transferring power through coupling rods to 3 driving axles. Total weight in working order 88.5 tons. Adhesive weight available for traction 59 tons. Starting tractive effort operating on steam alone 25,450 pounds force. The thermal efficiency this system could sustain, approximately 40%, exceeded every other traction type then in service on British railways. The steam locomotives it worked alongside were achieving, on a good day, 10. That difference is not incremental, it is structural. It is the difference between an engine that wastes what it burns and one that finds a use for heat that every other machine simply discards. KS1 made its first public appearance on April 22, 1928, at an Elnar rolling stock exhibition in Leeds. 21,000 people attended. The locomotive was among the exhibits. Initial trial runs between Leeds and Wakefield revealed problems. The boiler pressure, initially set at 180 pounds per square inch, was insufficient. The driver could not always judge the crank position precisely, and the engine occasionally stalled at top dead center. Kitson's engineers returned the locomotive to the Airedale foundry and corrected the layout. Boiler pressure was raised to 200 pounds per square inch. The locomotive returned to work on the Darlington to Starbeck run. Test loads were progressively increased from 183 tons to 403 tons behind the drawbar. On a gradient of 1 in 33, after a signal stop with the full load, the driver opened the regulator. KS1 restarted unaided. By 1933, reliability had reached the level needed for regular service. York Shed allocated KS1 to a daily goods working to Dairycoats and back. The engine men learned the machine's operating sequence. The oil burner raising steam for starting, diesel injection engaging at around 5 miles per hour, the exhaust heat feeding back into the boiler on the road. The fuel figures from those service runs showed consumption at approximately 1/5 that of an equivalent coal-burning locomotive. The engineering was working. Kitson and Company entered receivership in 1934. The Elner returned the locomotive to the receivers. It was dismantled. The question that remains is not whether the Kitson still was a success. It was a prototype. Prototypes carry problems. The question is what the engineering record shows and what would have followed from it. William Still had identified something that took the rest of the engineering world decades to rediscover, that waste heat recovery inside the power cycle itself, not as a secondary process but as a structural component of how the engine works, is where efficiency is found. He understood this in 1917. Kitson built it into a locomotive by 1928. Modern engineers shown the double-acting Still cylinder, steam on the inner face of the piston, diesel combustion on the outer face, exhaust gas circulated back through the boiler, describe the integration as genuinely counterintuitive. Combining two entirely different thermodynamic processes inside a single cylinder, making each one support the other, is a level of mechanical sophistication that remains unusual in traction. Engineering today. It was designed in Leeds. In 1917, the company that built it entered receivership in 1934. The engineers who understood the machine dispersed. The drawings dissolved into insolvency. There was one locomotive, no production fleet, no preserved example. The locomotive is gone, the company is gone, but the engineering record does not change. What KS1 did on those freight runs out of York, with its hybrid cylinders recovering heat that every other locomotive in Britain simply discarded, is in the Elner trial reports. It is not, generally, in the history books. That is what this channel intends to correct. If this is the kind of railway history you want to keep watching, subscribe to the channel. There are more locomotives, more railway systems, and more engineering achievements still to document. And if you have a connection to what you just watched, a family member who drove this class, worked in the workshops that maintained it, or operated on the railway that deployed it, tell us in the comments. What did they drive? Which railway? Which depot? Which line? The people who operated these machines are not in the standard histories, but the engineering record depends on what they remember. We want to hear from them.